I'm still paying you. I got the hard ass beats like the crack of the tech. I'm still paying you. Think y'all forgot what rap sounded like? I'm still paying you. Back to match up beats, the bang of the average. I'm still paying you. I'ma make y'all pay for
let's get started. Again, round of applause for DJ Cash, last class. Again, so we missed you on Monday, right. Tax accountant. And then what was the dude who showed up at my office?
He's just a crazy fan.
He said he was like your long lost brother or something stupid. Do you know that guy or?
No.
Okay. All right. Again, thank you so much for keeping it fresh this semester. All right, guys. So a lot to cover today. Plus we have a guest speaker at the end. So let's jump right into it. Again, Project 4 is due this Sunday. On Saturday we have the special office hours. Again, 3 o'clock, 3 to 5 in Gates on the 5th floor. Homework 6 is also due this Sunday as well. We will then release the solutions to it on Monday to prep for the exam, which is going to be on December 11th at 1 p.m. Not here, but in the Student University Center of the main auditorium. So again, we'll cover that immediately after this slide. And then if you want a TA next semester for this class, since we're not teaching 721, please sign up here. All right, any questions about Project 4, the final exam, or the homework? Yes. The question is, for Project 4, can you use late days? Yes. Other questions? All right, let's plow through this. Okay, so I will post this on Piazza, but I will have an additional office hours on the Wednesday before the exam in the morning and in the afternoon. All the TAs will have their regular office hours up until this Saturday inclusive. Then after that, they won't be available. If you can't meet this time with me, please send me an email and we try to make arrangements. And then I think Will also will be in town as well, and I'll see whether he can be available on Monday or Tuesday, depending on his schedule. So as I said, the final exam is going to be next Thursday coming up. You need to bring your CMU ID. You need to bring a pencil and an eraser, a calculator. Cell phone is okay, right? Do basic logs and things like that. And then just like the midterm, you can write on a regular 8.5 11 sheet of paper, handwritten notes about whatever you want in to study. Okay. And then there's a practice exam that's available that I posted on Piazza this week and also available on the website here. Okay. You can bring food if you want. I think that's allowed. Just don't bring weird shit. Like one year, somebody brought wet laundry. Don't do that. Somebody brought candles one year. Don't do that. I had a friend at another school. Somebody brought a therapy snake to an exam. Don't do that. Right? Be reasonable. Okay. All right. So the stuff that you need to be aware of that we covered throughout the semester, before the midterm, but we obviously need to build upon it throughout everything we talked about after the midterm. All right, are listed here. You obviously can't. We will not ask you a in-depth SQL question in the same way that we did in the midterm. You obviously need to be able to understand what select star from table does, right? Especially in the context of understanding the query processing models. In terms of how window functions are implemented, or how window functions are like the SQL syntax for it. I have not written the final exam yet, so I don't plan to write a window function question. Yeah, they're not hard. It's just a group by. It's weird, but it's group by. Again, the idea of the midterm is see if you understand the semantics of what the window function is actually doing. That's not what we've covered since since the midterm. We've covered how to build all the stuff to actually run transactions and run queries. All right, and then basic understanding of bus tub. Again, something very light, because obviously we can't have you write code and try to compile and debug it in the middle of the final exam. This is just to get a rough understanding of, did you actually do the projects, right? Again, we can't ask you on this file, what's this line of code? We're not going to ask you those things. It's more conceptual things. Okay. All right, so the main things we covered since before the midterm, we had the one class on the Monday before the midterm, we talked about join algorithms, and we talked about the 3 basic nested loop join algorithms you can have. The naive one, we just go and getting a block for every single tuple. That's stupid, don't do that. But we talked about how to do block nested loop join, index nested loop join. We talked about how to do sort merge join, building upon the external merge sort stuff we talked about before. Hash joins, the simple case, the partition case, and the hybrid hash join where you keep one hash table for the hot partition in memory, and then you let everything else spill to disk. And then basic optimizations for using Bloom filters and how to cost the joins in general. Right, sort of given set of tuples and a set of pages, right, and a given amount of memory buffers, can you cost how much it would take to run the join with, a start merge join versus a hash join? All right, then we talk about query execution. We did talk about query optimization. Actually, I'm missing a slide here. Query optimization, we talked about the basic high-level architecture of like top-down versus bottom-up. Again, we can't ask you for anything real in depth, but we also spent time talking about how to cost or estimate the cardinality selectivity of predicates, right? And using basic histograms. So you can expect to see a question like that. Again, it's not that difficult. We just look at the predicate, and then we can't ask you anything too in depth on this. So don't freak out about it. For the query execution, we talked about the 3 different execution models. Iterator, or the volcano model, it's calling get next, getting a single tuple at a time. Materialize is sending all the tuples from an operator up to the next operator. And then vector or batch is sending a batch of tuples instead of one at a time. And then we talked about the difference between a push versus pull query processing model. Right? Am I going to invoke at the root, call get next, and have that percolate down and pull tuples up? Or to start at the leaf nodes, run those operators, and send the data up the plan. We talked about the different access methods, sequential scan, the types of optimizations. Some of them we'll cover again today. Index scan, being able to take a single index or multiple indexes and run, evaluate predicates, and then how to handle update queries in our system. We talked a little bit about expression evaluation. Again, we'll talk about it again today. Just like, what does the tree look like? And how would you actually apply that on a per tuple basis when you run your queries? For query execution, we talked about the process models. There was a single process per worker, single thread per worker. What are the pros and cons of those? We talked about the different variations of doing parallel query execution. Right? Inter-query parallelism means that I can run multiple queries at the same time. Intra-query parallelism means that I can have, for a single query, multiple workers working together to process it. And then the difference between the horizontal versus vertical, the horizontal is when I have the multiple instances of the operator running on different workers to read or process data for different subsets of a table or subsets of the input data. Like if I partition it on ranges, I can have different workers working on different ranges. And then vertical partitioning is more, not as common, but this is where you could have one operator running some, doing some processing, and then they're streaming data up to the next operator who can run in parallel at the same time. And then we briefly talked about I/O parallelism, where we talked about what does the data system see when it has multiple disks? Could be abstracted away with RAID or an appliance. Or should the data system be specifically aware of, like, here's the different disks that I have and how to take advantage of them? And the most obvious thing is we didn't talk about it at the time when we talked about I/O parallelism, but like with write-ahead logging, a very common approach systems use is they have one disk for the regular tables and then another really fast disk for the write-ahead log. Because I want to get data out to the write-ahead log as fast as possible, commit transactions, and then tell the outside world that I committed. So I want my fastest disk to be for the logging. Okay, so I did have a slide. It was out of order, sorry. All right, I've already said this already. Query optimization, basic heuristics we can apply, predicate push down, projection push down. We won't focus too much on, we won't ask you anything about nested subqueries, don't worry about that. But statistics, cardinality estimations, looking at histograms, sketches, how to be able to say, for a given predicate on my table, here's some summarization of the data. What's the selectivity estimate for a predicate? Again, we can't ask you anything really complicated because we can't give you a giant, huge histogram. All right, and then we spent a lot of time talking about transactions. Right? We spent a whole lecture talking about the basics of ACID, atomicity, consistency, isolation, durability. Right? So understand what all those 4 attributes mean. What are those guarantees the system is trying to apply or provide for applications? We talked about conflict serializability, So how do we want to check for correctness to say that a schedule is going to be conflict serializable for the transactions that are inside of it? And how can we check whether two schedules are considered equivalent or conflict equivalent? View serializability is, again, a more fuzzy idea, fuzzy concept of serializability. But just understand what are the distinctions between view serializability and conflict serializability. So which one's more flexible, like conflict serializability or view serializability? View, right? But like, how to be able to identify that at runtime is impossible unless you understand what the application actually wants, right? So just being able to understand that some schedules may be still serializable, but they'll be view serializable and not conflict serializable. And a real system couldn't actually provide that. Then we talk about the isolation levels, right? The main ones in the SQL, at least the ANSI SQL standard, right? Serializables at the top. Then you have repeat or read, and below that you have read committed, and below that you have read uncommitted. And then snapshot isolation is this other thing on the side that provides certain guarantees that the other ones don't, right? And so what are the main anomalies that can occur for transactions on these different isolation levels? Again, could occur, doesn't mean that always will, but they could occur. And what are the mechanisms you would use to protect them?
Can we ever say that an anomaly will occur?
Say it again?
Can we ever say that an anomaly will occur in this particular?
The question is, can we ever say that anomaly will occur on our isolation level? So basically, you're asking whether could we predict for a given isolation level and maybe a set of transactions actually running that you will incur these things. Oftentimes it's like a race condition. Like in a real system, be able to say, like, if I run this, you know, like maybe one transaction will get paused because like a disk read or write or something, and then it gets stalled, and therefore it won't see certain things, it won't see certain anomalies. But like that disk stall isn't there, then it does see it. There's a bunch of layers. It's hard to be able to predict this, and that's why it's like it says it may occur, right? Because if I run and read uncommitted, but I only run one transaction at a time, then like it's technically serializable, right? There's some theory work on how to determine, I think, after the fact, whether a transaction saw something that it shouldn't have seen, and then try to then understand what are the long-term implications of that for data. Like if you, we're off topic, but like if my transaction incurs an anomaly, but then I write something to the database, then technically anybody that comes along later that reads and writes based on what I wrote is now kind of incorrect as well, like the butterfly effect. And how to measure that is like impossible. All right. So then we spent a lecture talking about transactions in the context of two-phase locking. Again, the idea of two-phase locking is that I acquire locks, either shared locks or exclusive locks, while in sort of the growing phase. And then as soon as I release one lock, then I automatically end up in the shrinking phase. But as we said, in SQL and real systems, there isn't an explicit call to unlock your locks or give your locks back. And so most systems are going to run either with strict 2PL or strong strict 2PL. Strict 2PL just means that I'm going to hold my exclusive locks until the very end and give them up all when I commit. But I'm allowed to release the shared locks earlier, just during the shrinking phase, assuming I can know how to get into that shrinking phase, or that I'm in the shrinking phase. And then strong strict 2PL, which is, I think the textbook might also call this rigorous 2PL. This just says that I'm going to hold all my shared locks and exclusive locks to the very end. So technically there isn't a shrinking phase. Just the whole thing's a growing phase. All right, we talked about the cascading abort problem. I think strong strict 2PL can avoid this, right? Because I'm not going to release my exclusive lock until I commit. So therefore nobody can read no other transaction can read my dirty read, and therefore I won't have a cascading abort. We talked about how to handle deadlocks either through deadlock detection or deadlock prevention. Right, deadlock detection was just identifying of cycles in the waits for graph, then killing a transaction to break, killing some transaction to break the deadlock. But you may have to kill multiple transactions to make that happen. And then deadlock prevention was the wound wait and wait die approach, where you order the order in which the transactions ordering based on the priority of their timestamp determines whether they're allowed or not, whether they can wait or not wait for another transaction that holds the lock that they want, and whether you're allowed to kill that other transaction and take their lock, or you kill yourself. Then we talked about the multiple granularity locking. So these are intention locks. Like in the hierarchy, I have at my top, I have a lock for my database or a lock for my tables. And within below that, I have lock for pages or tuples or even single attributes. So understand when you want to use intention locks or shared intention exclusive locks to minimize the amount of back and forth I have between my transaction and the lock manager, but also still maximize the amount of parallelism I would allow in the system. So the intention locks are like the hints for us at the higher part of the hierarchy to say what's going on down below. All right, then we talked about timestamp ordering transactions or optimistic concurrency control. Right, so understand what are the three phases in OCC. Right, you have the read phase where I'm reading and writing to the database, but I'm making changes to my private workspace. And then when the transaction goes to commit, there's a validation phase, and assume that for simplicity, you're going to run this with a single thread, and there's a single global latch that you take in the database to do this validation step to avoid weird conflicts to make your life easier. But understand what the differences are between backwards validation and forwards validation. Right, backwards is looking back to see transactions that previously committed to determine whether they wrote something that you didn't read, and therefore that would violate serializable ordering, and you kill yourself. And then forwards validation would be, did a transaction that hasn't committed yet write to something that, read something that I'm going to write to or try to write to, and therefore, since if they didn't see my update, if I commit, then again, that would violate the serializable ordering. Then we spent time talking about MVCC, multi-version concurrency control. We talked about the different ways to store the different versions. Right, there's the append-only approach, the time travel table, and then the delta records. Right, so understand the trade-offs, the implications of these three different approaches. Then the way you would actually maintain the version chain. You go oldest to newest or newest to oldest. Right, append-only can go both directions, and what are the pros and cons of those? Delta storage typically goes newest to oldest. Right, you put the old version goes in that rollback segment or the delta storage area. Understand what happens in garbage collection. How we find the tuples that are reclaimable and remove them. What happens when we remove tuples and need to update indexes? When does that happen? And how do we make sure that we don't have any conflicts when we do those things? And then there was a question on Piazza asking about MVCC with 2PL. So I'm going to quickly just go over that again. I think the textbook is saying one thing, and I'm saying something else. So this is the setup we had before. We have two transactions, T1 and T2. They get timestamps in the beginning. Right? T1 is going to read on A, and then it's going to write on A. And so the way this works is that there's no, you don't take shared locks on tuples because you want to allow a writing transaction to create a new version. But you can only allow one transaction to create a new version at a time. Right? So there's an exclusive lock, but it's on the new version that's being created. Right? So this transaction T1 is going to create a new version here, right? Add to this, and we set it, the begin timestamp to our current timestamp. The end timestamp is currently infinity, and since the previous timestamp, since we're going oldest to newest, is also infinity, we'll set that to be our timestamp. This is sort of bounding the visibility of this record. So now, if any transaction comes along with a timestamp less than 1, they would be able to read A0. Right, so then we do a context switch, T2 starts running, right? It reads A, and again, since its timestamp is 2, it's in the future, and logically it's in the future from T1, so therefore can't see the update yet, because T1 hasn't committed yet. So it's going to be able to read A0, because again, readers don't block the writers, and then when it tries to write to it, it wants to try to get the exclusive lock on creating the new version for the new physical version for this single logical tuple, and therefore it has to stall and wait. Right, assuming we're doing 2PL with deadlock detection. If it was doing 2PL with wound wait or die, again, that would T2 could potentially steal the lock from T1 and they have to roll back its changes. But assume we're just doing simple 2PL with deadlock detection. So then now when T1 comes back, it reads an A, it'll read its own write that it did before. That's fine. When it goes ahead and commits, then now that now its status in the transaction table gets updated. It's now committed. So now it would know that anybody coming along should be able to read this if they wanted to, right? And then now in this case here, it can create the new version. So to your point here, yes, and this here would be a this is an example of a what's that? So it's technically right skew because I'm reading something. I'm reading something that in the past where they were both seeing the same thing, but then I was allowed to overwrite it.
There's an anomaly.
What's that?
There is an anomaly. That was like
Yeah, sorry, there's an anomaly. Yes, and that's the whole point of like the to make it fully serializable. The extra step would then be like identify that you're trying to write to the same thing, and then you read something in the past that you should have read the other version, and you have to go kill that transaction. So there's if you want to get full serializability of this, there's a dependency graph you have to maintain as well. That's what Postgres does.
Just to be clear, it's not conflict serializable. We don't have conflict serializable.
In this example, no. Yeah. Even with regular MVCC without, with snapshot isolation, without the extra check, you make sure am I violating, do I have a right skew anomaly? You're not serializable. Like the fact you incur the right skew anomaly means you're not serializable.
What's the effect on performance that MVCC has on like PPL and OVC? Does it adversely impact that?
The question is, what does the effect of MVCC have on 2PL? Meaning what is the performance overhead of maintaining versions? I mean, there's pros and cons, right? The fact that I can read something without having it to, I can read an older version. I can have my readers not be blocked by the writers. There's an advantage to that, right? Like, is that worth it versus paying the overhead of maintaining the rollback segments and things like that, right? Or maintaining the different versions. You still have to maintain versions. Like with regular 2PL, I got to maintain versions anyway, but it's almost like UCC where it's my private workspace because I have to have my undo buffer. If I'm overwriting because it's a single version, I got to be able to go back and remove that, right? So I got to store the old version somewhere anyway. And so you could store that in the write-ahead log, but then now like if that gets flushed to disk and I don't have it in memory, now when I abort and roll back, I have to go back to disk, read back the write-ahead log and replay it, right? It's, there's no free lunch. All right.
Also, my second question was, the textbook says that MVCC with 2PL uses strict PPL.
The question is, the statement is, the textbook says that, yeah, I saw that. The textbook says that MVCC with 2PL always uses strict 2PL. So like, I think the textbook is wrong. So I'll post on Piazza. So I'm going by there's this famous textbook on nothing but transactions from Jim Gray and Reuter, the guy that coined ACID, and Jim Gray, the Turing Reuter, from the 80s that talk about how they do MVCC. And I don't, like their definition, it doesn't have to be strict.
So no, we should not assume strict.
The question is, should we assume strict? Any question on the exam will be very explicit, like what the protocol it is, right, to avoid any ambiguities. But like Postgres does MVCC with 2PL, and I'm pretty sure they're not using strict 2PL. SQL Server does strong strict, I think. Yeah, I'll post a link afterwards. Again, and the main takeaway is for any question, I would be very explicit about like, it's this protocol with this versioning and this concurrency stream and this here's the version chain ordering. Like we'll lay out things very in full detail. So there's not like, oh, there's not like, oh, it could be this, but if it's this, like I want to avoid all that. All right. Then after transactions, we talked about how to recover our transactions if there's a crash, right? We talked about the two main policies you have in your bufferable implementation, steal versus no steal. Steal means that I can write out dirty pages from transactions that I haven't committed yet out to disk. No steal says you cannot. Force says that when a transaction commits, all its dirty pages that are in the buffer pool have to be written to disk before you tell the outside world your transaction is committed. No force says you don't have to do that. So write-ahead log is using what? Steal no force, right? Because write-ahead log allows us to flush out the dirty pages from uncommitted transactions as long as the log records that correspond to the changes to those pages, as long as that's flushed to disk, then that's okay. We talk about shadow paging, again, understanding the pros and the cons of this approach relative to write-ahead logging. And then we talked about, again, how write-ahead log, the notion of these log sequence numbers permeate all throughout our implementation of our database system, including the buffer manager. And it's what I just said. I can't flush a dirty page until the page LSN or the newest LSN that modified that page until that's been written out to disk. And once that's flushed, then I can flush the dirty page. Then we talked about how to handle crash recovery, again, based on write-ahead logging. Like, there's nothing to recover in shadow paging. There's nothing to do. When you come back, the database is guaranteed to be in a consistent state, so you don't do anything. It's just write-ahead logging. We need to do extra work. And we choose to use write-ahead logging over shadow paging because the runtime performance is faster with write-ahead logging versus shadow paging. Right? But if you care about instant recovery, then you would do shadow paging. We talked about the different notions of checkpoints, so fuzzy versus non-fuzzy, right? And then within the fuzzy checkpoints, we talked about the dirty page table, the active transaction table, all the components we need to do the areas-based recovery based on checkpoints and the write-ahead log. Then again, we went through very quickly at the end of the semester, talking about distributed databases. So again, we can't ask you too low-level details. It's the high-level concepts that we care about. So what are the different system architectures? Basically, shared disk versus shared nothing. How we can do replication, multi-primary versus primary replica, or leader follower. Different partitioning schemes, horizontal partitioning. Then we talk about two-phase commit and Paxos. And again, that was the last class. We obviously went through it pretty quickly, so we can't ask you any low-level detail questions. How we do query execution, in particular, how to do distributed joins in our system. And then the semi-join optimization of just passing along Bloom filters instead of the actual entire data set. So last class, there was a question about, in the context of Paxos, in comparison with two-phase commit, how do we handle integrity constraint violations? And what I sort of messed up in the description of it is, the thing to understand about like two-phase commit is that you can have all of the, again, two-phase commit, all the nodes have to agree, the participants have to agree that we want to commit this transaction. And under Paxos, you need the majority. That means that if you're going to use Paxos or Raft, you have to have the decision of whether this transaction has violated any integrity constraints has to be figured out before you begin the commit process. So another way to think about it is like, it has to be a deterministic operation that like, we want to do this yes or no. And it can't be any ambiguity between the different nodes to say like, one guy says no because they're checking things at the moment after I've started the commit process. Right, so in two-phase commit, again, everyone has to agree to commit. So when this guy says, hey, we're gonna go to commit, prepare, and this guy says okay, and this guy says not okay, right? This is allowed to happen under two-phase commit because every node can independently decide whether this thing's allowed to commit or not, right? And so this is where you would check for the integrity constraint violations. In Paxos, what would happen, or in Raft, what would happen is the coordinator node, or I think the proposer node or the leader, they would determine at that point when we begin the commit process, this transaction has not violated any of the integrity constraints, therefore I'm allowed to commit. And therefore there's getting everyone else to agree that this is the order in which we're going to commit this transaction that has already passed our validation steps. Question, when would a particular participant abort? If somebody else tries to commit another transaction, and it says, I want to go next in the log. So again, it's a state machine. You're just trying to order the commits. And if there's like a split brain where, there's a network partition, each side wants to start, committing transactions on their own. And then when they form back together and it gets reconnected, somebody else thinks they're the leader and they try to propose to commit a transaction. But now you would have, if you allow that to happen, then one node would say it's transaction 1 followed by 2, another one would say it's 2 followed by 1. You can't allow that to happen. And that's why you have to be deterministic in the decision that this thing's allowed to commit at the moment you commit. Yes?
If your consistency constraints is like complicated and your data is like partitioned, then doesn't the process of checking the constraints already involve all the nodes communicating with each other, and at that point you just do some kind of...
The question is, if the constraints are very complicated, aren't the nodes going to have to coordinate with each other to, which would just be the same amount of overhead of running Paxos? So the dirty secret is in distributed systems, oftentimes they don't have the full integrity and referential constraints that a single node system would have. Oftentimes you don't get foreign key constraints in a distributed database because that checking is expensive. What's that? The question is, what about Spanner? I know Spanner gives you primary keys. Spanner gives you unique keys. I think they'll give you also foreign keys as well. Because if what's that? Say it again. Would they check it for you?
No, like
check. Oh, the check keyword in SQL. I mean, for the like check not null, sure, right? It's like talk about like when we call like alter table, create table.
yes.
Those checks aren't that complicated though. I mean, you can. It's the asserts. That's what nobody supports. You can do a global assert that says anytime I commit to this table, run this full query, and if it returns, if it returns anything, then I think it's a violation. So like as long as the query returns null, then my constraint's not violated. Nobody supports that in a distributed environment because that could just be a broadcast query to everyone for every single transaction you commit. So no one does that. But Spanner, I mean, we can double check. Spanner's going to be foreign keys, primary keys, basic check constraints. But oftentimes the foreign keys is the first thing to go, most systems in distributed environments.
Yeah, so Spanner, they have foreign keys, so that involves some internode communication.
The statement is Spanner has foreign keys that involve some internode communication. Depends on how the tables are partitioned.
Yeah.
If you have a student table and you have ID, and then I have an enroll table with student ID and the foreign key references to the student ID, if I partition both tables so that like student ID 123 and enrolled records for student ID 123 are in the same box, that's not a big deal. It's the broadcast ones that cause problems.
Yeah, but like that's application defined, you have to give some hints to the system.
For partitioning or for the foreign keys?
The partitioning by the foreign keys.
Yeah, so like oftentimes some systems will say like if you don't set the partition key to be the same as the foreign key, we're not going to check it for you. Okay. And whether or not that's okay for your application depends on your system. Okay. All right, so again, quickly, the things that aren't going to be an exam, any of the flash talks, any of the seminar talks we've had on Mondays or Tuesdays, those aren't the final exams. And then like, again, sometimes I go off the rails. We just had this, diatribe about Spanner. No, it's fine. I mean, Spanner is a fascinating system. It's like, I'm not going to cover it today, but like we can talk about it another time. But anything that like, oh, SQL Server does this, or MySQL does that, Postgres does that, that's obviously not going to be an exam. Because again, that's just like an example of a implementation of the concepts that we talked about throughout the semester. Okay? All right, any final questions about the final? Okay, so let's try to get through 721 we have what, 45 minutes? Let's see what we can do. Okay, so I showed this slide, I think in lecture 13 or so, where I said, here's all the ways you can make sequential scans go faster, right? We've covered all of these, except for materialized views and result caching. Result caching is basically says, if my same SQL query shows up multiple times and the data hasn't changed, I just cache the result and give it back to you. So I don't actually run the query, just give you back a cache result. And some systems will do that. Materialized view, these are more complicated if you want to do incremental maintenance. This is like if I define a materialized view, I define a SQL query, I want to cache the result, but then anytime the data changes, rather than just rerunning the entire query, I can do like an incremental update. For some things, it's easy, like a count with a group by on a key. Every time I add a new key for that, I increment the counter by 1. It's the joins are when things are complicated. Yes? The question is, will the exam take full 3 hours? No. You can sit around for 3 hours if you want, but it'll be the same, roughly the same length of material as the midterm. So hour, 20, right? And I would say because we chart this, because I love data, there does not seem to be a correlation between how long it takes somebody to complete the exam and their grade. So the person who usually finishes first, sometimes gets the highest grade, sometimes gets the lowest grade. And the person that finishes fast, the 1 year the person got a perfect score, and they finished the very end, right? So you take as long as you want. Say it again? No, we would write on the exam when someone turns it in. Yeah. Okay, so again, these are all the things we talked about the entire semester. Again, materialized views, again, these are hard to do. Like in Postgres, when you can declare a materialized view, it won't increment it for you. You got to call manually refresh, right? In some systems that can actually maintain them incrementally. So I want to focus on this down here. So we're 721 is typically about analytical systems, how to make how to build a system that run OLAP queries as fast as possible. So let's talk about code specialization and compilation. All right, so we have a really simple select query like this. Select star from table where key is greater than low value and key is less than high value. So the first thing is like, how do we organize our code to make this run as fast as possible without doing any special hardware tricks, right? And so we will be mindful of what modern CPUs look like and what they do for us, and then we can actually design and write code in such a way that maybe is not intuitive for us as humans to write, but it actually turns out to be the best thing to do for a modern superscalar CPU, right? So this is rough code that you would have seen in BusTop, right? Get it for every single tuple on the table, go look up the key, and then apply our predicate here, right? And if the key satisfies our predicate, then we'll copy the tuple in our output buffer. Right? Assume we're doing vectorized query processing, right? But if you've taken an architecture class, there's a problem here, right? Assume I have 1 billion tuples. I'm ripping through this. What's going to be the slow thing for us? Branching, the if clause, right? Because how does a superscalar CPU work? It tries to predict whenever it sees a jump, right, or a branch. It tries to predict what branch you're going to go down, right? Is this thing going to satisfy to true or not? And then it specularly executes the instructions because they're all within its pipeline. It specularly executes the instructions, assuming you're going to go down a certain path in the branch, right? And if you get it wrong, it's like OCC. You abort the changes you made, roll back, and then re-execute things again. We got to flush your pipeline to roll it back. So what you want to write in a modern deep system for superscalar CPUs is code like this, where I go get every single tuple in my table, and the first thing I'm going to do is I'm going to copy into my output buffer, right? And then later on, I'm going to check my predicate, and now I'm just going to do a ternary operation and between ones and zeros, and that's going to determine if both of these are satisfied to true, then the delta is equal to 1, and that's going to increment my counter of where I'm writing to my output buffer by 1. Right? I'm ignoring things when you break out of the loop, like check to see whether the last thing should even be there or not. But that's trivial code to write too. Yeah, like this question, why even need to turn a to do key less than 1, 0 and it? Yes, it would give you 1 and 0. Just being more explicit. The compiler will take care of that. Yes. Question: are you still branching? No. Assume the compiler gets rid of that, right? Right? And again, this seems counterintuitive to us as humans. Like I'm copying every single time, and then check to see whether I should have copied the last thing I copied. And then if it doesn't satisfy to true, then I loop back around and just overwrite the last one. And again, when I break out of the loop, I got to check the delta of the last one to see whether I should keep it or not. The question is, the copy might be really expensive as well. Again, assuming I'm operating on vectors of data in a columnar format, I'm ripping through columns. So this is a graph from the paper from the CW guys from a few years ago, but this is showing you the performance difference between these two approaches. So it's kind of hard to see. The blue line that loops at the top, that's the branching one, and the y-axis, sorry, the x-axis here is the selectivity of a predicate, right? So when the selectivity is 0 or less than 5%, then most of the tuples aren't satisfying my predicate. and the CPU's branch predictor is doing a good job figuring out I'm not going to need to go down to the branch. But then above some threshold, as it goes up, as the activity goes up, it's getting more predictions wrong. And so now you're paying this overhead of having to roll back the changes in your pipeline and go back. And whereas the red line, the no branching one, it's a fixed cost. So no matter what, I'm doing that copy, right, assuming I can do that efficiently, and then I don't pay the penalty of any branch or jumps because I'm just always doing it. And whether or not I overwrite the last one or not depends on whether the predicate gets satisfied to true. All right? So we're going to design code in this way. Again, it seems counterintuitive as humans, and the compiler isn't going to do this for you. This is something we would have to write. And most of the modern OLAP systems are going to do this. All right, so the next thing we've got to do is how can we speed this up even further, taking advantage of modern CPU instructions, SIMD. Who here doesn't know what SIMD is? Who here knows what SIMD is? All right, everyone does. Fantastic, good. All right, so here's our simple branchless version of the code before, and then now I'm going to vectorize it using SIMD, right? And again, this is pseudocode, but whatever. Like you load in a vector of tuples. I load them into my SIMD registers, and then I'm going to apply my predicate. I mean, I'm not defining how I'm going to do this in SIMD. I'll do that in a second. And then I'm going to take the output of those predicates that are sitting in SIMD registers, and I'm going to convert that back into my something I can put my output buffer, right? So give more specific example here. So say that I want to run this query, select star from table where key is greater than n and less than u, and then my table looks like this, like a simple vector, right? So what I'm going to do is I'm going to take the keys I want to evaluate. I'm going to load them into a SIMD register, and there's instructions explicitly to do that. And there's different sizes of SIMD registers, like 1024 or the new AVX 10 or whatever from Intel goes to 1024. AVX 512 is probably more common, so 512 bits. But you can say I'm storing, I can store either 4-byte values, 8-byte values. Sometimes they go down to 2-byte values, right? I have different lanes I can store things in, right? So I'm going to do my SIMD compare based on the constant that I'm trying to look up here. I'm going to get a mask, this will be a bit vector that says, here's the, for each lane in my SIMD register, whether the predicate evaluated the true or not. So I'll do that for the first part where key is greater than or equal to n. And I'll do that same thing for now the second part, the key less than 0. Now I have 2 bit vectors that correspond to whether the predicate evaluated true. So both of these are going to be sitting in SIMD registers. And now I have a SIMD instruction to do an and, again, cross the lanes, right? And then that's going to determine now which offsets in my input vector satisfy the predicate. So then now I need to convert this to something I can then use for identifying which tuples in my input vector satisfy the predicate. So I'll just maintain a vector of offsets, like in this case here is 0 to 7, just corresponds to offsets here in my input data. And then now I use a SIMD compress instruction that converts basically for any of the ones, or any one that's set to true in my input vector mask 3 corresponds to the offset in my offset array. And then now I get an aligned vector that tells me here's the offsets that satisfy the predicate. So I can rip through this super fast. And so now, again, that's now why I want to do the vectorized query processing model. The naming's bad, right? I'm using vectorized instructions to do this vectorized processing, but I'm going to also do this in the vectorized query processing model, or the batch model. So I can take a batch of these tuples, rip through it with SIMD, so my predicates can all be SIMD-ified, and I can do this very, very quickly. And this is what the co-founder of Snowflake, this is one of the big things that he helped develop when he built a system called Vectorwise that came out of CWI, again, same place where DuckDB is. And then Vectorwise got bought by Ingress for like pennies. And then he quit that, and then he hooked up with the 2 dudes from Oracle, and they founded Snowflake. And Snowflake was one of the leading systems that did this, but everyone does this now. All right, so another cool thing you can do with SIMD is all the other different operations we talked about throughout the semester, there's SIMD versions of them. Not all of them are as good not all of them can be easily vectorized with SIMD, because oftentimes when you fall out of the CPU cache, things get super slow because you have to go load and store to get to memory. But if you can align things nicely, you can do a lot of cool things. All right, so we talked about how to do probing in a hash table before, right? So the scalar version, the SysD version, for a single key, hash it, then do a single probe, and just do our linear scan until we find our match, right? So if we want to SIMDify or vectorize it, this is using what's called horizontal vectorization. There's a vertical one where you sort of look at things top to down, but this one's more common. So now I'm going to have in my hash table, with every single sort of row, I'm going to have 4 keys and that are packed together, and then I'm going to have my 4 values. And the keys themselves, I can store I need to have the original key because I have to do my check to see whether this thing matches when I land in my hash table. But since you have variable length keys, oftentimes what you'll do is also store as another vector in here, the fingerprint of the hash. So your hash might be 32 bits or 64 bits. Maybe I'll keep it like 8 bits around. So I can just do in SIMD very quickly, is my 8-bit prefix of my hash match the 8-bit prefix of this other hash? That's a single, you can do that very quickly. It's just integer comparison. If it doesn't match, then you know the full key is never going to match anyway, so you just ignore it. So now when I want to do a lookup here, I'll take my single key, hash it just like before, but then now when I land in a slot in my hash table, I'm getting back 4 keys in my example here. And now I just use SIMD to do the comparison I did before, get back a bit mask that tells me which one is matched, and then based on those, I can then go find the thing that I'm actually looking for. Why is this faster? Yeah. So the question is, why is this faster? Because when I go probe in the hash table, that's a cache line lookup. I'm going to go get 64 bytes, right? And so for that 64 bytes, if I can put more things in there, then do SIMD comparison instead of having to do for loop one at a time, this is way faster. Because otherwise, it's like, say, if it's a SysD loop, like a for loop, I'm going to go for each element. Say I need to look at 4 keys. I'm going to look at each key separately. That's one instruction. Whereas in SIMD, I can do all 4 in a single instruction. Yes, you have to load in registers, right? But like, also too, I'm showing like 4 lanes. With AVX512, assuming you have like 32-bit integers, you can put a lot more, right? This would be like 120-bit registers, which is like Intel had in the 90s. The question is like, you're amortizing the cost because most of these are fail. Yes. Yeah, so like it's way faster to use SIMD versus SysD for this. And again, the trick is instead of just trying to, like my example, I was trying to match, going back here, I'm trying to match on single keys at a time, right? Or single elements of a key, like a single character. So my keys might be kind of large. So instead of doing the SIMD comparison on the full key, which if they're variable length, it may not be the same for every, for all the elements in my bucket of 4 that I'm getting within the slot, I use the hash prefix, and that guarantees they're always this fixed length. All right, so what I've shown so far of how we take the data out from one operator, or one sort of step of an operator, and pass along to the next one. This is called using what are called selection vectors, right? And the idea here is that when the operator is going to spit out, it would be offsets into my input vectors that correspond to these are the tuples that I want to pass up to the next operator, right? So it'd be like fixed length offsets within my input array, right? You can also, some systems will do bitmaps instead. So think of this as like there's a 1 or 0 corresponding to whether a tuple within a batch that's being passed up from one operator to the next, whether they've satisfied the predicate and they should be continued processing as you go up. So maybe the case and you saw this in the bus stop projects, maybe the case I pass up a vector and I apply some predicate, but only one of them is going to match. So I need a way to represent how I then pass up that batch and say, ignore all the other ones that don't match because they didn't match down below, only look at this one. And then sometimes what you want to do is have a staging buffer to say, I get up 1024 tuples, but only one of them match. So instead of me passing up a 1024 tuple or 1024 buffer that it only has one tuple matching, I'll just wait for more things come below me then fill up the buffer, and then send up a dense buffer going up. And different systems do different things. There's trade-offs for all of these. Yes?
Are there systems that do this like adaptively?
Question, are the systems that do this adaptively? No. You could, but like you basically have to implement two of them, like two implementations. All right, so that's using SIMD and to and modern hardware to speed things up. We don't talk about GPUs. In the previous version, 721, that is actually becoming a hot area now. There was a bunch of GPU databases last decade. They kind of didn't go anywhere because they had to store all of them. You had to store the entire database down in the GPU card, right? With NVLink and some of the newer stuff NVIDIA is doing in newer versions of PCIe, this is changing. And I can't say too much, but there's some major things happening within next year. You'll see a bunch of more GPU databases coming out. So, basically, it's the same principles they talked about with SIMD will apply in the GPU world as well. That's what I'm mentioning. All right, so I'm going to talk about how we do code specialization now through code generation. So in BusTub, the way it works is like you're given a query plan, you basically walk the tree, and then within that you get an expression tree, and you have to walk that to produce, to evaluate predicates and so forth, right? So there was a very famous project called Haiku out of the University of Edinburgh in the early 2010s, where for a given SQL query, they would generate the plan, and then they would convert that plan tree into actual machine code, C code. They would then invoke GCC to then compile that function to run that query into a shared object, link it in, and invoke that. So you don't do that in the interpretation you would do in BusTub or like Postgres and other systems. Now I basically have a hard-coded program that executes exactly what my query wants to do. And that's going to be way faster because I don't have to do jumping, I don't have to do traversals or follow pointers in a query plan tree. It's hard-coded, baked for doing exactly what the query wants. So here's what, again, this is what BusTub would normally look like. If I scan through my table, I got to go get a tuple. I got to figure out what the tuple looks like. I go to the catalog and get some stuff, and then I apply my predicate by running all these steps. So instead, what I want to do is I want to have a program that basically hard codes in. Here's the tuples I'm looking at. Here's the predicates I want to consider. And here's the offsets to go find the attributes that I want. And then now I'm just running CPU instructions to do these computations and not worry about trying to interpret what's the size of the table or what size of a tuple and how to jump into my slot arrays to find things that I want. I can rip through things way more efficiently this way. What's that? The question is, can we just use an off-the-shelf compiler like GCC? In the example, yes. In most database systems, except for the Germans, they're going to use an off-the-shelf compiler. The question is this fast enough? No. So we'll fix that in a second. Actually, maybe we can jump to that now. Yes, question. Is any system try to use a JIT system? The Germans, yes. And what they do, I should have told this. What they do is, the first version, they in Hyper, they would, query shows up, instead of emitting C++ code or C code, they would emit LLVM IR. And then they would let the LLVM compile that into machine code and run that. Because it was faster to run to generate the IR rather than C, because then you invoke GCC, and that's slow, right? In the newer version in Umbra, which now also is commercialized as CedarDB, and I'll have slides for this, what they do is they emit their own IR, and then they have another pass that can convert that IR into assembly that they roll by hand. Then they run the assembler, which is fast and cheap to do, and then they start running the query based on the assembled version. Then in the background, they run LLVM to compile their IR into like machine code with like O3 turned on, which that can take second or milliseconds. And the idea is that if the query finishes with the assembler version, then you're done, right? But if it's still running by the time LLVM finishes, then they slide out the assembled version and plop in their compiled shared object. Like how does it, like the way they orchestrate the system to get work done, it's like they schedule tasks. Like when it goes and says, all right, I want to run this task, it would say, all right, I need to do this operation on this piece of data is my compiled version ready? If yes, invoke that. If not, invoke the assembler. Insane, right? So this sounds amazing. I would say, though, we built an LLM-based query engine that did this just-in-time compilation stuff. It's a nightmare to debug. And we'll see this when we talk about Databricks in a second. Like, you got to have people that know about compilers, and they got to know about the databases. And then now when you crash in these systems, because it's like dynamic code being generated for a query, you're not landing in like, well, if you generate C, you can do this. But like if you're doing the JIT compilation going directly for LMIR, then compiling that, when you crash, you land there with symbols. Without symbols to know exactly, here's the line of code in your C++ application that generated this IR that caused this crash. It's a nightmare to debug. So but what generated the IR? That's the part you got to fix from the dataset, right? And so the Germans, they wrote their own debugger so that they can reverse back based on Mozilla RR to reverse back like here's the line of code that generated this IR for me. Like you would think the guy's on cocaine, but he's not. It's insane, right? Like his vice is apple juice, right? And it's one guy. Right. So to the point, like, is this compilation thing expensive? Yes. And this is actually not a new idea. IBM did this back in the 1970s with System R. They would generate the assembly for a query plan, and they would run that. But again, they had the same problem that any time that the system crashed, you had to go figure out what assembly created this assembly to figure out what was the mistake. Actually, I think System R was written in C. So it's the same idea. Or the other problem is every single time you change the API, the storage system, then you got to go change all the compiler code. Right? Because again, it was early days, they didn't have good abstractions. So an alternative is to what Vectorization came out with, and again, what Snowflake does, and what a lot of systems follow along, is do what are called precompiled primitives. And the idea is that in your database system source code, in your repository, you pre-bake and automatically generate all these primitives for different predicates you may evaluate for any particular query. Like integer column equals integer column less than integer. Right? Think of all of those separate operations as a separate function that you then have. You can generate all these through templates in your code base. And then when you compile the binary, within that binary itself is now all these different primitives that you then stitch together at runtime based on what the query wants to do. And then now you don't worry about jitting things because you have basically things all together and you're kind of assembling the building blocks for a query plan just through pointers. The statement is the orchestration cost could be high. Yeah, so the jump call is expensive. Aha. But if you do batches of tuples, then that amortizes the jump call. That's how you get it. If it's doing tuple at a time, no. If it's a batch tuples, again, what the Snowflake guy he figured out, like this is how you can do this. All right, so say my query like this. Again, I'm doing a string column lookup on ABC and integer column lookup on 4, right? So I would have a separate primitive to take a vector of tuples in to do string column equals something, or constant. And in this case here, I would have another one for the integer column. But now you see it. Now I'm passing along the positions offset. Right? So I can chain these things together, take the output of one, and then feed it into another one, and then it would know that should I if this position thing is if it's not my position vector, then I know I should ignore it in my input column. So even though the number of possible permutations you can have in a query plan for these predicates is infinite, but in actuality, it's actually a finite number, right? There's only like so many different data types, so many different things you can do with them, right? Something equals something, something less than something, and so forth, right? Something equals a column, two columns are the same, right? So this is what Snowflake does. This is what Photon does in Databricks, right? The current research says this is the right way to build your systems, not do the JIT compilation stuff. Yes. Question: do you need to have a cogen framework? Yeah, but it's not hard. No, it's not. Like here's two right here, right? Like something equals something, something less than something. It's not. You only have a certain number of data types. And the reason why this is better than JIT compilation, because now if there's a bug in this primitive, if it crashes, then I can go through GDB or whatever and go walk through and figure out how to reproduce the crash. All right, we got 10 minutes. I can't cover all of these. Let's do a vote. We'll pick two. I'm going to keep count. Raise your hand if you want BigQuery. Raise your hand if you want Snowflake. A little more. Raise your hand if you want Redshift. Very few, okay. Raise your hand if you want Yellowbrick. I might override you because Yellowbrick is insane. Raise your hand if you want Databricks Photon. All right, that's a clear winner. And raise your hand if you want ClickHouse. All right. We'll do Databricks. Oh, shit. All right, we'll do Databricks, Yellowbrick, and I'll try to get ClickHouse quickly. ClickHouse is a quick thing to mention. ClickHouse people already gave a talk. All right. Let me show one thing about Snowflake. The dude that wrote, again, I keep mentioning this guy, Marcin, who like invented all this stuff, invented like the vector stuff, the SIMD stuff. This is how hardcore he is about databases. This is a photo I took, and this is his leg. He got the Snowflake tattoo because he loves his database so much. That's how serious people are about these things. And you think I'm crazy about databases? Like he's in there with me. Okay, Databricks. So Databricks is based on Spark. What was Spark written in? Anybody know? What query language? Or so what programming language? Scala. What does Scala run in? JVM. JVM is terrible. Don't use it. Right. So they had this problem where they had this original version of this thing, Spark SQL, that was doing the JIT compilation stuff. They would emit Scala bytecode that would then compile to the JVM, but then they found themselves struggling with getting good performance because you got to get people, again, who know compilers and know databases and also know how to deal with the JVM. So they spent more time trying to modify the code to generate to do instrumentation in the JVM rather than making the query engine go faster. Right? Because again, Spark was originally written as a tuple at a time, row-based system. And obviously, again, with Snowflake and all these other stuff we talked about throughout the semester, we know we don't want to do this. So what Photon is a runtime written in C++ that connects into the JVM through JNI, the Java native interface. And then at certain points when they execute a query, they recognize I have a C++ version of the thing you want to do, like something equals something. They can then hand it off to the C++ code, who then could run that more efficiently, and then send the data back into the JVM, right? So there's a paper called Photon. I'm just pointing out here, there's a bunch of my former students, and students have taken 721, or sorry, 445, like you guys. They're all, a lot of students at Snowflake, and a lot of people work on this project. All right, so what is Photon? It's shared disk aggregate storage. It's doing pool-based vectorized processing. Precompiled primitives expression function we talked about before. We won't talk about the query maps too much. But again, the core idea that Photon is doing is these precompiled operator primitives or kernels, the same thing I just talked about with Vectorwise and Snowflake. Right? They generate all the possible things you could want to do on data. They precompile them, and then at runtime, they're stitching them together and to recognize these are the things I can fall out into the C++. And if they don't have a C++ version of it, then it just falls back and runs the JVM version as they normally would, right? And they comment how, again, in their experience, it was much easier to build the C++-based engine, that these precompiled primitives, than it was to instrument the JVM and do just-in-time compilation. So even though the first version of this, of their implementation, wasn't as fast as the JIT version was, but they spent all the time now actually making the precompiled stuff actually faster, and they get bigger improvements and got faster than they would have if they were still mucking around the JVM. I don't know for the numbers here. I mean, it's quite significant. There's other tricks they do. Like they assume that even though column may not be declared as not null, but the column might be declared as supporting nulls. They assume maybe it's not null, so there's a bunch of checks they avoid, and then if they get it wrong, they roll back. There's some things like that to do as well. The question is, can I just keep in the summary table that I don't see any nulls? If I'm reading a bunch of Parquet files or CSV files that I've never seen before, I don't have that. So I got to guess. There's other tricks you can use, like JSON, like since JSON's untyped or barely typed, you can say, oh, I know that like most of these times in this field it's going to be an integer, and then only if you see a string then you fall back and do something else. All right, so they're going to do a technique called also expression fusion. So we talked about operator fusion before. We can kind of take the if I have like a scan with a predicate, instead of having them be two separate operators, I can put the predicate inside the scan operator, right? So that's operator fusion. They're doing expression fusion because they're doing these predefined, these precompiled primitives. So instead of having the two functions that I showed before, where I'm one predicate's doing the check on the, on the first part of the conjunct, and the second one's doing the second part, they can just pre-generate a bunch of these ones that can do both together. Like they could rewrite this query into being a between clause, and then now it's one less function call to go process all the data, right? Another cool thing they do with the shuffle phase that we talked about before is that they can determine whether one partition gets too full because the data is skewed. Then they can, after the shuffle completes, they can go back and repartition it again, kind of like the recursive partitioning we talked about with hash joins. So say that I have my worker filling up all these partitions, right? And then I recognize that these three partitions are underutilized, and the one in the middle over there and the one in the end are kind of getting too full. So what I can do is I can dynamically say, all right, I'm going to start rewriting the data that I have in these guys into this other one to fill that up, and then just pass along the next three. So then I can sort of automatically downsize or upsize the number of workers I have after each shuffle phase based on the data I see going in. All right, let me talk about Yellowbrick just because I find it super, again, this is super fascinating. So it's a new engine written in C++. They forked it about 10 years ago. And I said this in a class. I said this about them in one of these lectures at some point, and I forgot I said it. And then when I went to go visit them in London a few months ago, they told me what I said, and then their marketing people love it because they actually sell it to customers based on what I said. So Yellowbrick does things like the Germans you would only do if you were on cocaine. The amount of system optimization they're doing, you would not want to do if you're a brand new startup, but this is what they did. So what is it? It's a shared distributed storage system. They're doing push-based vectorization. They're doing transpilation, the cogen stuff we talked about. Instead of generating LLM-IR, they're generating C++, and then GCC compiling that, but they can hash that. But then the engineering stuff they do is insane. So they have a row store that's based on Postgres at the front end. Query shows up. If they have the cached query plan, they reuse it. Otherwise, they'll compile in the background and then run it when it's available. What's insane, though, is the communication channels that they have in between the object store, which is like S3, and the different workers themselves. So these guys said that the NVMe drivers and the hardware drivers that Linux gives you, or the hardware vendors give you, were way too slow. So not only did they have to build the runtime engine for the database system, they wrote their own kernel drivers for the NVMe drives they were running on and for the NICs. And then TCP was too slow, so they wrote their own network protocol based on UDP to make that go fast. But then copying data from the NIC down the hardware through the kernel up into user space, that's too slow too, because the kernel's slow for us. So they're going to use what's called SPDK or DPDK to do kernel bypass, where they're managing their own TCP IP stack in user space and don't let the OS do anything. So when Yellowbrick turns on, they call malloc, get a bunch of memory, take control of the hardware, and they never talk to the operating system ever again, because the operating system is going to ruin your life. And these guys took that to the extreme, right? If you're a brand new startup, you would not do this. This is insane. But this is what they did 10 years ago, because they were coming from the fintech world. Question, how's it different RDMA? I mean, RDMA is sort of the same thing, but you need specialized hardware for this. For DPDK and SPDK, you don't need specialized hardware, right? You can run that on Amazon. Yes? The question was really quick. There's another one from Stanford as well, but like there's other ones. They did this 10 years ago. Yeah, it's not standard, but like, so that if you need specialized hardware, it's not gonna work in the cloud, right? You can use UDP everywhere. All right. The last one you guys wanted was ClickHouse. All right. So I want to say quickly about ClickHouse. So this came out of Yandex. I think they started building it actually in 2009. And when the guy gave a talk, like as I said, like when ClickHouse became public, I thought it was fake, not because it was Russian, because it was like the things that they were listing they were doing was actually kind of at par or a little more advanced than what Snowflake was doing at the time, back in like 2016. And it seemed insane that this company I've never heard of, I heard of Yandex, but this system I've never heard of just showed up on the block having all these amazing features. But again, it's something I've been working on for a while. So again, they're doing pull-based vector query processing. There's a shared network architecture, although you can support the cloud stuff, the S3 stuff as well. They're doing, they'll compile the expressions the same way that Postgres does. Their query optimizer is not very good. They know this. They publicly say this is something we're working on. Their query optimizer is actually terrible. The Postgres one is probably better. But for the things, they're doing single table queries. It's okay. It's the joins that cause the problems. I want to talk about what they do for hash joins, but in particular on the hash tables. So ClickHouse comes with 24 different implementations of hash tables. Nobody does that in their system. Even the Yellowbrick guys aren't that crazy, right? Because they have specialized hash tables for every single possible data type that you have. So I'm going to show one graph here. Right, this is doing a join with a group by. This is from a paper from a few years ago, but this ended up making it into the real ClickHouse system. It's just showing that they have all these different. Actually, they don't have all of these, but the one that they added here is if you have trying to do join on strings, a linear probe hash table, just the off-the-shelf one, is not going to perform that well. But if you have different hash table implementations, think of doing compile time optimizations, how to pack the data into the slots based on different sizes, whether you exceed a cache line or not, then you can get much, much better performance. So this is sort of like the pre-compiled primitives that we saw. If I'm doing a comparison on this key on this type or this constant, I can have a specialized version of that function to do that comparison. They're basically doing the same thing, but for hash tables for all different possible data types and the lookups you want to do on them. And that part's super amazing. They do a bunch of SIMD stuff as well, where they try to have different versions of different operators that are SIMDified for different versions of SIMD on Intel. So there's AVX 512, AVX 256. Sometimes the 512 one is not as fast as the 256 one, because the older CPUs would actually throttle down the frequency because they overheated. So they would be able to detect and say, I'm going to run the AVX2 version, the 256 version instead of the 512, based on what hardware they're running on. It's amazing. All right, so let me switch over to the RelationalAI speaker. We're over time. But again, the main takeaway from all I want you guys from all of this is that these systems are doing it's amazing stuff, and try to get things run as fast as possible is really challenging to do. Got it. All right, so remember the Haiku system we talked about before? They did that early compilation stuff? This is the same school. They're very strong in databases. Leonard, thank you so much for being here. The floor is yours. Go for it.
Okay, so I'm starting, right?
Yes, go for it.
Yeah, okay. Right, okay. So do we understand SQL? And if not, why? Right, okay, so I'm spending just a couple of things about myself. So I'm spending most of my time at RelationalAI, and I represent RelationalAI Paris, and I'm also part-time at the University of Edinburgh, where I was full-time for 2 decades prior to RelationalAI. Okay, so last time RelationalAI was here in presenting the CMU. So we talked about REL, which is a programming language that we developed in RelationalAI, specifically a programming language for relational data. If you're interested in that, you can see there was a recorded talk by Wim Martens, about 10-15 minutes, and also there was a paper in Sigmod with details of the language. But we did not, in that talk, we didn't fully explain what were the SQL problems that we tried to fix. And that by itself would require a very long talk. But what I'll try to do today in the short time that I have, I'll try to give you a taste of SQL problems that we are that we're trying to fix. Okay, so you all know what SQL is, right? Okay, so it's like the language for relational database. It was a standard since '86, international standard since '87, implemented all over the place. If you look at the top programming languages according to IEEE, so this year it's at number 4. If you look at the job ads and which jobs require knowledge of SQL, last year it was number 1. This year it's fell just below Python at number 2, right? So now SQL has been with us since '86. It was standardized, and there were several standard went through several iterations. '92 was when it was basically reached its current shape. And after that, we now live with SQL 2023. We are on the way to produce SQL 2027. There are a whole bunch of additions in between. It's not free. If you want to buy it, it will make you about $2,000 a quarter. And it consists of 11 parts, which are numbered by random numbers between 1 and 16. So don't expect it to be consecutive. There are actually reasons for this, but not for this talk. And what all DBMSs implement is essentially the core, which is the part 2 that's called SQL Foundation. There are some discrepancies, plus something else from the standard, plus something else not from the standard, but that's the world we live in. All right, who designs it? It's a committee with this fantastic name, ISO IEC JTC1 SC32WG3. Again, each part of this name actually has a meaning. So that's the picture of the committee from its last meeting in Barcelona just a couple of months ago. Right. And the way it works is that, so most of the technical work happens inside another organization called INSIGHT, which stands for International Committee on Information Technology Standards. Despite the name international, it's actually very US-centric. Though half of the committee is from Europe and Asia, but you only can be in this committee if you represent a US registered entity. So discussions in this committee lead to papers that are then forwarded to the international committee that meets a few times a year. Then basically decisions are made in that committee, people vote, first in the committee, and then the papers get incorporated into draft standards. And then the national bodies, so each nation will have its own standards committee. They'll vote to approve those standards. This vote happens in several stages, and eventually that's why there is such a clock, usually 4 or 5 years between additions of standards. And eventually the standard is approved. And then the fun begins. Okay, let's start with a little fun, something that you all know about SQL, all learn about SQL. I have two relations, R and S, both have single attribute A, and I ask you to compute the difference between these two relations. Let's not worry about multisets. Let's not worry about bag semantics. Let's say everything is a set. Okay, there are 3 ways you can do it. You can just directly use SQL except operator to compute the difference. Or you can use a subquery. You can say, give me everything in the relation R that's not in the relation S. Or you can use exists for a subquery. You can say, give me everything from relation R such that there does not exist something in the relation S that's equal to it. So if we ask you students, to write this type of query, you will write one of those, and you would expect to get full marks. Because you run it over the set and say, okay, well, same answer. They're equivalent queries. In fact, lots of SQL programmers think that they're equivalent queries. But let me change a little bit, and let me replace 2 with a null in this query. And then suddenly, what I get is 3 different answers. Right? And I can assure you that huge number of people who write SQL queries, they fall into similar traps, right? They change not in, not exists, and, suddenly you can see that there's a very dramatic difference between writing it with not in and not exists. All right, so we have a bit of a problem, right? But let me tell you that we have actually even a bigger problem with understanding SQL. What is simpler in SQL than select star, right? The first thing that you do, like you learn SQL, select star from R, right? From some table, you see the table. Okay, so I'll make a claim that absolute majority of SQL programmers actually don't know what select star does, right? So let me explain this on an example. So, okay, so let's say we have a relation R, again, single attribute A, value 1, and I write this query, like repeat attribute A twice in the output, right? Okay, so that's going to give me this relation with attribute A repeated twice. Every DBMS will give you the same thing. Now I say this, let's use it as a subquery and say, let's select star from that subquery. Like I literally plug this query queue from above. I just plug it into this line in front. And I ask you, what this query returns? And in my experience, actually, of talking to people directly, I ask this, and even like talking to students when I teach in front of the class, and people start guessing and say, well, maybe it will return the same as before, maybe not, maybe it will give an error. What's going to happen? I mean, this is one line query with select star. A relation has one tuple, and people start scratching their heads. And there's a very good reason why they scratch their heads, because the answer to this question depends on which system you run this query. Postgres and SQLite will give you one star, will give you basically as above, but Oracle, SQL Server, MySQL, and DB2 will all give you compile time, and DuckDB now will all give you compile time error. Okay, already like one line queries, select star, we are getting into trouble. But now let's get into more trouble. Okay, I ask, okay, let's run this query. Give me everything from R where the condition is that this query Q prime, the one that we just saw, that sometimes runs, sometimes gives a compile time error. And when this query returns something, what will this do? Most people say, oh, well, probably, it will give you R if it runs on Postgres and SQLite, maybe compile time error if it runs. If it doesn't run, the answer is no. It will always give a relational, right? So you see, the thing is that like with this super simple queries, I can start like with super simple devices in SQL. I can start writing queries that even experienced SQL programmers will start questioning what's going on. Okay, let's come back. More fun with nulls. Let's say I have a database that has orders and payments. All right, we have order, and we know that sometimes some of the orders have been paid. And I ask you to write a query, give me unpaid orders. Okay, give me all the orders for which there is no payment. Fine. This is very simple query. Let's run it in SQL. What we are going to get? Well, in this database, we are going to get that order 2 and order 3 are not paid. Right? We know intuitively it's wrong because we know that there are 2 payments, right? It's, how do we know that both of these order 2 and order 3 are not paid? We don't know this. It's quite possible that one of them is actually paid, but SQL will tell you that order 2 and order 3 are unpaid. Imagine then you go and chase the customer and say you didn't pay. The customer say I paid, and then then the customer never comes back. So we get what's called false positives, right? So answer that we know it's not true. And actually, these false positives, they're fairly common, right? So we try to experiment a little bit with TPCH-like queries and populate database with nulls, and these false positives pop up all the time, right? And I also would like to point out that, most of the time you see graphs coming from Sigmod papers, but this is a very unusual creature. It's a graph that comes from a PODS paper, from a theoretical paper. Okay, so nulls are all over the place. Right, if you are European and you want to go to Texas and you ask for the weather, they tell you don't ask about Celsius, only Fahrenheit. You can be asked for a payment on your multiple nulls, and this is actually a screenshot of a real database of a big retailer, right? And you can see the lab nulls, and nulls cause problems. Like there are like all these stories about actually it's a real story about a person whose last name is null and who cannot do anything in this life anymore. Now that everything has to be recorded in a database in not null fields. And so when nulls appear, we know that things kind of go bad, right? Like in textbooks that add that, well, null treatment is fundamentally at odds with the way the world behaves. Books for sick database professionals tell you get wrong answers to queries, you cannot trust answers. And like there are even like headlines, like, this is from BBC, that children heart surgery halted by incomplete data, right? So it could be quite dramatic. Okay, so there's one other question that I want to briefly address, and this is how standard is the standard? All right, we have the standard. We assume that everybody has to do the same stuff. But actually, if we run multiple queries on different databases, we know sort of from experience that some of them will give you different results. So we try to quantify that, and from a random query generator, about 2% of queries from the most basic fragment, they behave differently. Some issues, admittedly, are just minor and very syntactic, but some are serious. So I'll give you 2 examples of serious issues, right, of things that could be unexpected.
Right, we're kind of a little over time. We're over time. Okay. Sorry.
Okay, it's 10 minutes. Okay. I'll just wrap up with this, right? So, and basically, and say, why we find these questions problematic in SQL? Because SQL standard has been growing crazily, right? It started with 10-page codes paper, then 100 pages per SQL standard. Now we're at 4,500 pages. There is not a single person in the world who knows everything. And what we are trying to do in RelationalAI is to have a different approach, to have a small, well-defined core language with a clear semantics, and then extended by libraries. So this is our approach. This is what LanguageRel is.
All right. So again, for the 2 things. Again, this is the last class. See you guys on Thursday next week. And then the last thing also too is that we got a announcement from Farnham this morning. And the good news is that DJ Cash won Most Dank DJ at Carnegie Mellon University this year. So a round of applause. Can you get a photo? Here. So, here. Yeah, handshake. You got it. Awesome.
I think so, yeah.
Awesome. All right, guys, give a round of applause to Didi Cash. Thank you, Leonard. And then good luck with your final exams and everything else. And then again, Saturday office hours, Sunday project due, Thursday next week is the final exam. Okay?
Cash money, flick flips, acrobats over tracks. 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 Get the fortune, motherfucker fame. Maintain but never strain, flow with the grain. Get the fortune, motherfucker fame. Maintain but never strain, flow with the grain.